Now, if we keep moving forward, when we start looking at the actual atom and how we had to kind of like numerically divide it up into what it is, we have some different numbers we work with. Okay, the first is called the atomic number. Okay, the atomic number is basically the same as the protons. All right, so atomic number and protons means the exact same thing. All right, when you look at a periodic table, we find the atomic number. Usually it's sitting either above or next to kind of the actual symbol for it, but it really isn't standardized where you're going to find it. Every table is a little bit different. Take a look at the one in the room as you're watching the video, or if you're watching at home, pull up a periodic table and take a look at it. They're all in a little bit different spots. But the one thing that's always the same is the atomic number is always the smaller of the two numbers, and it's always the whole number. Okay, and the periodic table is always will count up from 1 all the way up to 118 in sequence, from left to right, top to bottom, because it goes by the atomic number. Okay, so that's our protons, is our atomic number. It can also identify the electrons if you have a neutral atom, okay, which means it's not a charged atom. Okay, charged atoms, we call them ions. In those cases, we have more or less electrons than protons. But to be neutral, okay, the protons, which are positively charged, have to match the electrons, which are negatively charged. So for a neutral atom, the atomic number can also represent the electrons, but only if you're neutral. Okay. Now, there's a way we can shorthand note this, okay? So if you're looking at the symbol for an atom, and we'll go to the board here, what we can do is, if we take something like carbon, there are 4 kind of quadrants that we write stuff into up here, okay? And each kind of spot is a little bit is kind of reserved for a certain kind of thing, okay? So when you do shorthand notation, the bottom left-hand corner, so for carbon would be a 6. That's reserved for the atomic number. Okay? And we'll fill in the other ones as we kind of go here and talk about the other ones. Actually, it might not be a bad idea to fill a couple of them in now since we're doing it. So the top right-hand corner, this is reserved for any charge that you might have on, be a plus or a minus kind of charge on it. We put in here. So it could be maybe a 2 plus or a 1 minus or a 3 plus or 2 minus, whatever the charge happens to be, that's what we put on the end. That's what we put for shorthand notation. The bottom right-hand box is used for how many. So if we have 4 carbons, we would say 4. If we had, let's say, C6H12O6, the number of atoms we have always follows in that bottom right-hand subscript. Okay, so that's what this is for. And the top box, we're going to get to that one in our next slide, but I'm just going to give it away now. The top box is for the mass number. Okay, and the mass number is basically taking your protons plus your neutrons gives us our mass number. So for carbon, it's one of 3 options. It could be carbon 12, it could be carbon 13, or it could actually be carbon 14, because there's actually 3 different versions of carbon, or 3 different isotopes of carbon. So every little quadrant kind of has its own little meaning when you do shorthand notation for that. Okay? Now, that does bring us to mass number. And mass number, like we just talked about, is talking about taking the protons plus the neutrons. Okay? First, most importantly, absolutely, you got to remember this. Do not forget it. This is not the atomic mass. Okay? I promise you somebody will mix this up. Mass number and atomic mass are very different things. They sound similar. They both have the word mass in them. They both are talking about atoms, but they are very different in terms of how we use them and what they represent. Okay? So it is not the atomic mass. We'll get to that later. This is the mass number. Mass number is not on the periodic table. Okay? It is not a number that you're going to find sitting on the periodic table anywhere, because the periodic table, it gives us an average of stuff. It doesn't talk about individual isotopes. Okay? And mass number does that. It takes the protons you have or the neutrons that you have and it adds those 2 together. Okay? So for example, for carbon 14, you'd have 6 protons and 8 neutrons. For tritium, which is a form of hydrogen, you'd have 1 proton, 2 neutrons for a mass number of 3. Okay? Now the way we add that up, it's always just your protons plus your neutrons. Now what's nice about having a mass number is, if you know the mass number of your substance, you can find neutrons, which is sometimes hard to locate because neutrons are neutral, and we don't usually see them in any of our shorthand notation stuff. Okay? But if we know we have carbon 14 and we have carbons of 6 for atomic number, 14 minus 6 would give us 8, which then would be our number of neutrons. Okay, so if you do need to find neutrons, one way to do that is mass number minus atomic number, or mass number minus protons will give us your neutrons. Okay, so then here again is our symbol for mass number sitting up here in our shorthand notation. Now, as we work through these units of atoms, they're so incredibly small that using grams and mass or kilograms is really challenging for us because the numbers get incredibly small. Let's take a look. If you take the mass of a proton, it is 1.67 times 10 to the negative 27 kilograms in its base unit. Okay. Now, nobody really wants to do math with numbers like this. Okay, it's a pain in the butt. It just is. No one likes it. We don't want to do it. So, of course, what science does, we say, hey, let's just set a whole new scale or a whole new set of units to make this work. And we'll just say that this number is equal to 1. Okay, and we call that 1 AMU or 1 atomic mass unit. Okay, the beauty is this. Out to 3 significant figures, neutrons have the same mass as protons. Now, they're not perfectly identical. There are slight differences, but at least to this precision, they're the same. So we could say that the mass of a neutron is also 1 AMU. If you take a look at electrons, electrons are even smaller than protons and neutrons. They're actually in a whole different subclass of subatomic particles than protons and neutrons are. Okay? So their mass is 9 times 10 to the negative 31 kilograms. So basically 1/2000th of an AMU. It's actually so small of a mass that when we calculate the mass of an atom, we often ignore it. Okay? We say that that mass isn't enough to really matter at all to us. We actually just kind of exclude it. So the cool thing is, if we can exclude this, then we can start looking at, let's say, carbon-12. Okay, carbon-12, 12 is its mass number, which means it has 6 protons and 6 neutrons. So as a result, we get 12 AMUs. Okay, this will become useful for us as we get further into our chemistry and start dealing with AMUs and moles and grams and kilograms and kind of making these units collide with each other through some stoichiometry or something called in-dimensional analysis. So we can actually see this, that as long as we can use the scale of atomic mass units, that allows us to basically add our protons and neutrons to give us our mass. And of course, we can always convert back to kilograms if we need to on here. Okay, so carbon-12, being that it has a mass number 12, you know the protons have to be 6 because carbon is always a 6 because that's its atomic number. So then it must have 6 neutrons in it also. All right.